as we move forward to learn how to solve the Schrodinger equation, we're going to first learn some properties that the wave function must satisfy. And these will come from things we already know and some new things as well. So as we go forward, we're going to restrict ourselves to time-independent potentials. So we'll look at the time-independent Schrodinger equation shown here. And we want to come up with methods to solve the Schrodinger's equation and how psi is constrained. And again, first of all, we're talking in this scenario, this part of the course, where psi is representing the probability to find the position, and it's a continuous function because x is continuous. So recall the wave function psi of x gives us the probability density. P of x is equal to psi star psi, where to find the particle per unit length. And we know the probability is normalized, meaning that if we integrate the probability density over all x, again, we're talking only about a one-dimensional problem here, that has to equal 1. That means the probability to measure the particle somewhere on the x-axis is 1. The particle exists somewhere on the x-axis. And again, substituting in, that implies that the wave function is normalized as well. Then we integrate psi star psi over x from minus infinity to infinity, we get 1. Another thing with this is going to help us is that as we go to infinity, plus and minus infinity for x, the probability density and the wave function must vanish. Otherwise, we wouldn't be able to make it normalized. And just think about that. If the probability density and or the wave function doesn't go to 0 at infinity, that means there's finite values at infinity, and that can't integrate to 1. There's no way. So those are things we know from before. The other one is the wave function must be continuous. And this is going to take a little bit of effort to convince you, but the wave function is a continuous function. So let's take a look at that. So first, let's examine the wave function for a free particle. And again, we're just going to look at the time-independent part psi of x here. Well, we should have talked about the free particle before in terms of the general, the full wave function, but here we'll just concentrate on the free particle. And so the Schrodinger equation simplifies in that case, and the way we want to solve this is just multiply those constants through, so we have the derivative on one side and everything else on the other. Just makes it easy to solve. So the second derivative of psi is equal to this constant here minus this constant. E and h bar are positive constants, and so is the mass, times psi. That is a simple solution. Again, it's a very basic differential equation, and the minus sign tells us that we have to have complex exponentials because of that minus sign. If we take two derivatives, we're going to take two factors of this coefficient down, and that means that we're squaring it, and there's no way that can be negative unless we have an I in there. So we can represent it this way as complex exponentials. Again, we should be general. It could be plus I times square root of 2me over h bar times x, or minus. Another way to represent it is using the Euler relation is to write it in terms of sines and cosines. This is often what we will be doing as we go forward, but we can represent it either way. These are equivalent, where these coefficients need to be adjusted to go back and forth. So we have a cosine of 2me over h bar squared square root times x plus the sine. And again, here we had the plane wave state, which is the free particle that has a definite momentum. And it was e to the ikx minus omega t, so we have k is equal to the square root of 2me over h bar squared, and e is equal to h bar omega. Those are relationships we should already know from before, but this is just reaffirming that. But that's not important, really. What we care here is that these are smoothly varying functions. They're sines and cosines, and so they're continuous. That's what we care about. So with that alone, we can't really build up anything. But the point here is that these plane wave states, or the free particle states, are important to build up more non-trivial waveforms. So what we do is we make superpositions of wave functions size, and we use different momenta or energy, either way, and that will allow us to make some non-trivial waveforms. So to do this, I'm going to bring in an app from fallstad.com, which I will post on the course site, and let me make sure this fits here. So here we go. So we have this app here. A moment. And right now, what I'm doing is showing a sine function. And the way to interpret this is the waveform we're talking about. This is the frequency spectrum here. So I'm talking about one wave here of 220 hertz. And I can play the sound if I want. If I turn the sound up on my computer, you can hear that. That's one. Okay. We don't care about that sound so much. Well, we will come back. And again, this is a continuous waveform. Now, the thing is, like I said, we can make non-trivial waveforms by just adding different amounts of these. And so we can add that. And again, we can just do random. I'm just doing a random here. So, and it is periodic, meaning that this pattern does repeat itself. However, notice it's still continuous, right? So again, there's a pretty. Let's listen to what this sounds like. Again, let me get that. Ooh, that was not pretty. So we can keep doing that, and we can build. It turns out we can build just about any periodic function by doing this. So let me come back to the sine function here. And now, really, what we care about, or actually, let me come back to the. One moment. Let's go back to here for a moment. But this is how we build up non-trivial solutions by constructing out of these plane wave states. Again, when I say we have constant frequency, that means that we have a definite value of the momentum, or the energy, really. So we're going to add up different waves of different energies. That's what we're doing here. In the quantum mechanical sense, this one represents a wave of a free particle, if you will, of one energy, or momentum. This is another one with a little bit higher energy. And so we go up here. That one's a higher energy as well. So we keep adding those. And we can make all these kind of pretty much any solution we want out of this. And this is an important part called Fourier analysis of quantum mechanics. And some people say that quantum mechanics is nothing but Fourier analysis. So what we want to do now is consider a discontinuous type. So let's consider a square wave. So this is a discontinuous wave function, and I'll come back here. And so, but again, to generate it, let's show it. They have it here. Go to square wave, and notice this is what it looks like. And let's just listen to it for fun. Ooh, that was not pretty. But again, it's not a pretty sound. But this is a It's a discontinuous waveform. But notice though, here's the important thing. Notice the edges. The edges here there's this little there's a little vibration here. It doesn't quite exactly match a square wave. Well, what happened? The thing is, that's because we're only using a finite number of sines here. And remember, this is the distribution, the amplitude, and the frequencies we need. But notice if I increase the number of terms here, what happens? It gets closer and closer to the actual one, and I'm going to use fewer and fewer. So if I use fewer and fewer, notice it's quite away from. Oops. And if I increase more terms, the closer it approximates that square wave. And there's only a finite number of terms I can generate here. So what that means is to actually get the actual square wave solution perfectly, we need an infinite number of these plane wave states and added in a particular way to get that square wave. So that's the point here, is that we need an infinite number of those terms, and each one has a different energy, and increasing energy as we increase the frequency, which means that we need an infinite energy contributions coming into this. So that's why a discontinuity is not a physical thing, it's unphysical. So that's why we do not allow, at least in any ordinary situation, these kind of discontinuous wave functions. They're unphysical. And so our conclusion is the wave function is continuous. So that's what we're going to conclude. Okay, the next, and I believe the last, is that the derivative of the wave function is continuous. It varies smoothly. There's no kinks in the waveform. So again, if I just try to draw that, that means it kind of looks like this. That's it can't look like this. That would be a discontinuity in the derivative. And what we think about that is that the derivative is infinite when we have a kink like that at this location here. That's where the derivative is, we could say, infinite. If you're a mathematician, you'd say, oh, it's undefined, but okay, whatever way you want to say it, we're physicists, we're going to say it's infinite. And when we look at the Schrödinger equation, now notice that this derivative, this second derivative here, is going to be infinite. We'll say infinite, or undefined if you like, but for the moment we'll just say it's infinite. That means that we have e is equal to minus infinity plus some finite term v times psi, which says that the energy is infinite. Again, we could just say the energy is undefined if you like. So the conclusion is that the derivative of the wave function is smooth, and actually it's infinitely differentiable, which means it's really smooth. We'll take that. There's one caveat here, which we're going to use in our first significant example, and that's if the potential is infinite at any point, or there's a transition from an infinite potential to a finite potential, we're going to relax this last condition. And again, it's unphysical, but it will really help us build intuition about quantum wave functions and actually how to solve these. So these are conditions. And we are going to use these in the next one to examine a particular scenario and make sure these are adhered to. The wave function is continuous, the wave function is smooth, all derivatives are finite. As we go off to infinity, the function must taper off to 0, and the wave function is normalized. These elements will help us solve the time-independent Schrodinger equation.